Foundation Models for Embodied Decision-Making Agents, Part 14. Today I'm discussing a presentation by Nikolay Atanasov at MIT. He is from UC San Diego. Nikolay's presentation is, in a nutshell, how can we add heuristics to the deep learning stack in robotics? And he has three levels that he discusses: the robot model, the environment model, and the task model. So what his goal is in general in this presentation, and if you look at his research, it's how to enhance end-to-end deep learning stacks with heuristics, whether it's physics, whether it's LLM type semantic information. So his goal is to use engineering tricks, mathematical tricks, whatever, maybe trick's the wrong word, but ideas from different fields to enhance the, to enhance the end-to-end stack. So in that sense, this is an interesting presentation because it's going a little bit away from this data-driven, data-only type environment into more, how can we reduce the search space? So, for example, if we use a Hamiltonian to model the robot, what that means with Hamiltonian, this is a concept from physics, which just says, look, we can maybe add a function for the dynamics of a robot. We can add a function for the physics that a robot is exposed to. So that way, the robot doesn't have to learn those physics in a very intense data-driven context. This is the idea, right? The same with the environment, and most importantly, in task specification. So, for example, in the task specification context, he talks about LLMs. Actually, go pick up the knife from the kitchen, right? Now, that could be learned end to end through millions and millions of iterations, or it could be maybe used more efficiently or more sample efficiently. It could be trained more sample efficiently by having the robot have a semantic understanding of what a kitchen is, what a knife is, what a drawer is, and then just pick up that knife from the drawer if that's the task. Same with the environment. We spoke about Grace Gao just recently about semantic maps. For example, my self-driving car picks up my son from school. Now, over time, the car can learn to pick up my son at a specific location that might not be as risky as maybe other locations, because at this particular corner of the street, there's a construction, or there are people playing with a ball, or there's a dog, a jittery dog. So those are semantics that can be learned, of course. And excuse me. Everything can fundamentally be learned through data. The problem is you have a very large search space that this data has to go through to learn all these things. So maybe we can build implicit heuristics. We can add explicit heuristics, or we can sort of help the model by having, like, for example, Hamiltonians. So there's three sections in this. Nikolay talks about three particular levels of modeling. One is the robot, one is the environment, and one is task specific. So let's talk about the robot itself. So we could use Hamiltonians to enhance the physical representation of the robot. What that means, Hamiltonians, we know that from physics, it's the combination of energies that a system is exposed to. So the goal is really to enhance end-to-end learning with physics to reduce the search space. Hamiltonian dynamics, okay? It reduces the search space. It adds physics to the model, and those physics can be learned too, but the model doesn't have to implicitly create those hierarchies. Now, if we look at large language models, this is not how they work, okay? So I'm comparing this now to large language models. Because the OpenAI researchers, they said explicitly that they think the way the model operates is that it starts learning tasks. So it kind of starts to build implicit hierarchies or implicit representations of reality. Let's use the analogy of large language models to explain this. So in a large language model, we have the ability to program. We have the ability to fill in words. We have the ability to translate. We have the ability to summarize a poem. But those tasks were not explicitly modeled. Those tasks were implicitly learned. So what Nikolay is doing is the exact opposite. He's building explicit, he's adding explicit heuristics into the model that is modeling the robot, adding, let's say, Hamiltonian dynamics to reduce the search space. Now, the argument here, why that's a good thing, is because we have so many more degrees of freedom, but I'm not so sure. I'm not so sure about that. I feel that we have, there's an argument to be made that that is not necessary, that all we need is a lot of data, that we need a better representation of data. And there's an argument to be made, no, I mean, we can accelerate. Why use massive amounts of resources to do something that can be accelerated? This is the argument. I don't want to take more time here, and also I don't want to make a claim because I'm not in the trenches, but that's what Nikolay is working on. The same with the environment. Take the environment, right? Take the environment, and I think I spoke about this particularly when I discussed Grace Gao's idea of semantic maps, right? We can learn implicitly semantic maps. We can do that. But the amount of iterations we need and the amount of data that we need to go through is just immense. So why not just use large language models to represent some of the semantics? The same idea here, right? The same exact idea. Nikolay talks about this actually specifically. He mentions semantic maps using LLMs. I'm actually at the Weights and Biases event here in San Francisco. I just spoke with one of their AI researchers, and this is definitely happening. This is happening. The robotics community is jumping on this. Basically, semantic representation of the real world through LLM. Why not? We have a compressed understanding of the world that we've learned in the internet. Use that to help navigate robots. So this is the concept. This is the idea. I've spoken about this, about the Tesla Full Self-Drive, but the Tesla Full Self-Drive is using a map that is based on location data. And that mapping is fine for finding A to B, but it's not fine for semantic reasoning. Semantic reasoning implies much more than just location data. Again, we could learn that implicitly. We can definitely learn that implicitly, but it's just going to take a lot more time. One idea that he's discussing in the environmental model is sign distance functions. So that is just, imagine you have an occupancy network and you simplify it by having, let's say, a +1 if you're away from the object and a -1 if you're inside the object. So the 0 would be the actual surface of the object. So again, this is a heuristic. You can learn how to circumvent an object end to end, and that's what Tesla did in their Full Self-Drive, at least according to their end-to-end party line. Whether that's true, whether they're using sign distance functions, whether they're using ellipsoid representation of objects, which is helps mathematically to be more efficient when representing, let's say, 2D data in 3D, things like that. Those are all open questions. It's not clear how exactly Tesla is doing what they're doing, but fundamentally, Nikolay is offering solutions to a physics problem that can be helped heuristically, and therefore the search space can be reduced. He's talking, the last thing I want to talk about here is the task modeling. And that to me is actually an interesting thing, because that to me goes towards the Robinson Crusoe robot concept. What that means is, well, think about it this way, right? You have a robot that is trained to do tasks, or take an LLM. An LLM is trained to do certain tasks. How could we induce the machine to figure out which tasks would be most appropriate at a given time? So this is a sort of a higher level problem where we're going towards the Robinson Crusoe robot here. So instead of telling the machine what to do, we have the machine figure out itself what will be the best use of its resources at a given time. Now, of course, that implies a certain goal-oriented or purpose-oriented worldview. For example, the Robinson Crusoe machine that is dropped on an island needs to have some sort of survival bias or something. I mean, it's not just going to come up with solutions for survival like Robinson Crusoe or the character that is stranded on an island is interested in survival. Like, that's why he does all the stuff he does. If somebody gets dropped in the Amazon jungle, they will try to survive. So we humans have that sort of overarching purpose. In this case, that's not so clear, but that's not the main conversation in this task modeling segment of Nikolay's talk. Is first, how can we model robot control? There's something called, think about robot control as a sort of sequence of logic functions. There's a name for that, something temporal logic, I think. So it just means that, look, your task is to walk from A to B and open a door. And you could formulate that task in sort of Boolean algebra logic, which is if you're, if you're here, then you're not there. If you're not there, then here. If you're here, then or. So you have not, and, or, and you have the key, you don't have the key. You have the key, if so, then you can turn the key and open. If not, you have to go find the key. If you have to go find the key might be here, here, or here. Where is it? If it's not here, it's there. So you can sort of segment the whole search space of the robot and its actions in logic. And this is one of the things that he's presenting in one of the papers, which is, by the way, a pretty old paper. This goes back to control theory. But it's part of a stack that he's suggesting, which is LLM. So use LLM to describe a task, translate it into an automaton, which is that logic function that I just discussed, and then execute the task. This is the idea. So it kind of goes into the realm of, okay, let's say we use LLMs for semantic understanding of the real world. Let's say we do that, right? How do we actually implement that? And Nikolay offers a solution here, which is we have a LLM, which then translates into a sequence of logic, and that sequence of logic translates into action. What I like about Nikolay's presentation is, first, it's a sort of anti-end-to-end stance. Or maybe anti is too strong of a word. It's, look, we don't have to learn everything from data and build hierarchies implicitly. We can use some knowledge that we've gathered. We humans have gathered a lot of knowledge in the last couple thousand years of evolution. Why can't we just use that? Now, this is orthogonal to the idea of OpenAI, which is have as general a model as you can and as much data as you can. And I'm pretty sure that Elon Musk is soon going to come up with some sort of doctrine, a la, the no LiDAR doctrine, and here it's going to be no heuristics doctrine. I'm pretty sure something like that is it's already happening in the robotics community or in the AI community in general. We have the people who say, look, why not use heuristics, versus the people say, no, let's not use heuristics because we don't want to constrain ourselves. So in that sense, I think Nikolay's presentation opens up questions, maybe even open-ended questions, but it's worth thinking about this. It's worth thinking about, look, where do we use explicit heuristics? Where do we use models that help? Can we build models that accelerate the buildup of intrinsic heuristics or implicit heuristics? And finally, on the task modeling, I think let me just use a tangent here. Douglas Hofstadter's "I Am a Strange Loop," right? What is he saying there? In that book, he's talking about the I, and the one thing that the I represents is maybe a virtual, maybe a illusionary feeling of this is something I want to do, right? This goes back to also Sam Harris, right? The illusion of control, or whatever. What is it? The illusion of free will, right? This is very fundamental on that front, because so do we have free will or we don't have free will? Well, if we drop Robinson Crusoe on a deserted island, it seems to me that he seems to, I mean, this Robinson Crusoe at least is exerting some sort of free will, because he's going to build a whole set of things that help him survive. Now, in that context, the Robinson Crusoe robot is going to do the same thing, and therefore it has free will. But how do we build a machine that has that sort of free will, that has that ability to come up with its own tasks? So it's, think of a large language model that helps you get good grades in school, but you don't have to tell it how to do that. It does that on its own. It says, hey, I just did the summary of this book because I think your teacher might want to know about this, so you might want to learn about this. To me, this is an open. So this task modeling goes into that direction, and I find that's a very fascinating area of research. So to summarize, Nikolay's presentation is an attempt to bring back some heuristics into the modeling space of robots, in particular Hamiltonian physics, environmental segmentation, and semantic mapping, and then finally task modeling. And this opens up the most interesting question in this whole context, which is how can we design a robot that has the ability to pick the task or the knowledge it has according to the situation that it's exposed to. Thank you.